In this example, we'd like to calculate the relationship between an applied force P and the motion at the point at which we're applying the force. So we have a tension compression bar with cross-sectional area A and Young's modulus E, and we'd like to consider the deflection at this point here and determine its relationship to the applied force. And the way we're going to do this is by conservation of energy. So the work in is going to be equal to the work stored. Work in, since it's a linear elastic system, is going to be 1/2 P times delta. And the work stored is going to be the strain energy inside the system. And for this particular problem, what we're going to do is use the kinematic relationship, so the integral from 0 to L of 1/2 AE times epsilon squared, integrated along the length of the bar. And the reason for that is that for this type of system here, we know what epsilon looks like. So in fact, the motion, u, as a function of x, we know is linear out to a, starting at 0, and linear back down to 0 at x equals L. So the deflection here, delta, looks like that. So I know that epsilon in the first segment of the bar is equal to delta over A, and in the second segment it's equal to delta over L minus A. So the work stored I can write as an integral 0 to A, 1/2 AE delta over A squared dx plus integral A to L 1/2 AE delta over L minus A squared dx. So we can integrate both of these expressions here. Everything in the integrand is a constant. So from the first term I have 1/2 AE over A delta squared, and from the second term I have 1/2 AE over L minus A delta squared. So setting that equal to 1/2 P delta, I can solve for P. So P is equal to delta times AE, and rearranging the fractions we get L over A times L minus A. So this provides a relationship between the applied force P and the motion delta.